Welcome back to Physical Science 101. This is our third lesson of Unit 7. In the last lesson, we talked about processes that give us radiation, processes that give us alpha radiation, beta radiation, and gamma radiation. In this lesson, we're going to talk about measuring radiation, we're going to talk about the effects of radiation on the body, and we're going to talk about half-lives, the time for radioactive decay. Let's start with measuring radioactivity. We're going to have 3 units for radioactivity. Actually, we're going to have 6. We're going to have 3 new metric units, so standard metric units, and 3 old obsolete units that are not supposed to be used anymore, but you might still see them. Let's start with a measurement of radioactivity. Our unit of radioactivity in the metric system is the becquerel. And 1 becquerel is 1 decay per second from a source. So if you have a radioactive source, and that radioactive source has 1 decay per second, then that source would have a radioactivity of 1 becquerel. Now the old unit is a curie, and 1 curie is actually 37 billion decays per second. So 37 billion becquerel is a curie. That is actually a lot. So a radioactive source with a radioactivity of 1 curie is highly radioactive. Normally in the laboratory, we will have sources with microcurie radioactivity. So thousands of becquerels, as opposed to billions of becquerels. So that is our first unit for measuring radioactivity. It tells us how radioactive something is. Okay, so that's how radioactive something is measured in the units of the becquerel, and 1 becquerel is 1 decay per second from that source. The old obsolete unit is a curie, and just remember that a curie is a lot, a lot of becquerels. It's billions of becquerels, so that is a very radioactive source. So that measures the radioactivity of a source. The next 2 units that I'm going to talk about are measurements of radiation dose, so the dose of radiation that someone receives. So the first is talking about the source, the second is talking about the person, the dose of radiation that a person receives. The unit for a radiation dose in the metric system is a gray, and 1 gray is a joule of energy deposited in a body per kilogram of body weight. So the larger you are, the more mass you have, the lower the radiation dose is for the same amount of energy. So 1 gray of radiation dose is 1 joule of energy per kilogram of body weight. The obsolete unit that you might still see around is the rad. So a rad is 1/100th of a gray. So that's radiation dose. Radiation dose is 1 gray is 1 joule per kilogram, and the old rad is 1/100th of that. Now, the gray is used often in medical contexts, medical research contexts. For determining the effect of radiation on a body, there is something called the equivalent radiation dose. And the equivalent radiation dose is measured in units of sievert. So 1 sievert of dose is 1 gray of dose times a weighting factor. Now the weighting factor takes into account the fact that different radiation has different effects on the body. So for some types of radiation, you will have a weighting factor of anywhere from 1 to 20 or so. So types of radiation that are more damaging to the body have a higher weighting factor. So the sievert is actually the unit we're going to consider when we talk about the effect of radiation on the body. So it's called the equivalent radiation dose. It's the dose of radiation that you get times a factor telling you how damaging that radiation actually is. So the equivalent radiation dose is 1 sievert in the metric system. The obsolete unit for equivalent radiation dose is a REM. That stands for radiation equivalent to man, radiation equivalent to man, REM, and a REM is 1/100th of a sievert. Okay, so we measure the radioactivity of a source with the units of becquerel, and obsolete, that would be a curie, and the equivalent radiation dose, the effect of the radiation that a person receives, is measured in units of a sievert, or obsoletely, a REM. So what are the effects of radiation on the body? For this, we have to consider two different cases called an acute radiation dose and a chronic radiation dose. An acute radiation dose is when you receive a lot of radiation all at once. So if you're exposed to a source for a short period of time, that would be an acute radiation dose. And a chronic radiation dose is a radiation dose that you've received a little at a time over the course of your lifetime. So chronic is radiation that you receive throughout your lifetime. Acute is from a single or short period exposure. So for an acute radiation dose, if you receive an acute radiation dose of less than 0.25 sieverts, there's typically no effect seen. So less than 1/4 of a sievert, you're pretty safe. 5 sieverts, however, is a lethal dose for 50% of the population. So if you receive a radiation dose of 5 sieverts all at once, that gives a 50% chance of your dying from the radiation. A 10 sievert dose is certain to cause incapacitation and death. So less than 1/4 of a sievert all at once, you're safe. 5 sieverts, it's a 50-50 chance whether you're going to die, and a 10 sievert dose is almost certain to cause death. So those are for acute radiation exposure. So if you receive a dose of radiation all at once, that radiation will affect your body depending on this scale right here. 5 sieverts, 50-50, 10 sieverts, almost certain death. That's an acute dose. For a chronic dose, the concern there is cancer. So you're going to receive radiation throughout your life, and that adds up. And the way that it adds up is for every sievert that you receive over the course of your life, you have a 5% probability of developing a cancer. So for a chronic dose, you add up all of the sieverts of radiation over your life, and every sievert gives you about a 5% probability of getting cancer. Okay, where does this radiation come from? So here are some sources of radiation that you might be exposed to and the dose that you can expect to receive from them. Let's start with living near a nuclear power station. If you live near a nuclear power station, you can expect to receive something like 1/10,000th to 1/100th of a millisievert per year. So milli is 1,000th of a sievert. And so every year you can expect to receive a dose like that. That's from living near a nuclear power station. Living near a coal power station will also give you a dose of 3/10,000ths of a millisievert per year. You might ask yourself, why is that? Well, coal, when they dig up coal from the earth, they dig up radioactive elements with the coal, and when that is burned, those radioactive elements go into the air and give a dose of radiation to people living nearby. Now, these are still pretty small doses. Sleeping next to a human 8 hours every night, that's 2/100ths of a millisievert per year. Why is that? That's because we have radioactive elements in our body as well. All of the elements that make up our bones and things like that do include some radioactive elements. So we also give off radiation ourselves, and if you're near someone, you will receive a dose from them as well. You can also receive radiation from the sky. This is called cosmic radiation. This is radiation from space. And that will give you a larger dose of 24 hundredths of a millisievert per year, so about a quarter of a millisievert every year. The ground will also irradiate you. Radiation from the ground is about the same, about a quarter of a millisievert every year. Natural radiation in your own body, as I said, that's about 4/10ths of a millisievert per year. So there are all of these sources of radiation, and they're all cumulative. So you have to add up all of the sources of radiation that you're exposed to, and then multiply it by the number of years that you've been exposed to them to come up with the total chronic dose of radiation that you've been exposed to. The United States Capitol building, the granite, once again, dug up from the earth, contains some radioactive elements. That will give you almost 1 millisievert per year. There are atmospheric sources of radiation, which is mostly radon. That accounts for 2 millisieverts per year. Now, for those of you in Louisiana, the good news is we don't have a whole lot of radon here. The ground underneath us is not very radioactive. Fortunately, the ground underneath us is mostly sedimentary, and it does not contain a lot of radioactive elements. So here in Louisiana, we have to worry about hurricanes, but one thing that we don't have to worry much about is radon. We don't have to worry about radioactive radon collecting in our homes. That is a concern in many parts of the country, but fortunately not here. So if we take all of this together, the average individual background radiation dose for an American is about 3 millisieverts per year. So 3 millisieverts per year is the individual background radiation dose. So those are from all the natural sources. The total average radiation dose from all sources for an American is about 6 millisieverts per year. So every year, on average, you'll be exposed to about 6 millisieverts. So you multiply that by the number of years, and you can calculate your chances of getting cancer from radiation. Some other sources of radiation. If you fly in an airplane, you are closer to the cosmic radiation. So people who fly in airplanes a whole lot, like airline crews, actually will receive an elevated radiation dose from cosmic radiation. Smokers will receive a much larger dose. Smoking a pack and a half a day will give you somewhere between 13 and 60 millisieverts per year. What goes on there is, once again, when the tobacco is grown, it draws up minerals from the ground, and some of those minerals are radioactive. And the bad thing about smoking is that you then put those minerals in your body. So they are in your body. There's no way for you to distance yourself from them or nowhere to shield yourself from them. So you are exposed to that constantly. So when you smoke, you're putting those radioactive elements right in your body. The radiation limit for nuclear workers is about 20 millisieverts per year. Now, during the Fukushima emergency, there was an emergency limit, elevated limit. Those people were allowed to be exposed to 250 millisieverts per year for working during the Fukushima emergency. So these are many, many different sources of radioactivity. I skipped one. Background radiation in parts of Iran, India, and Europe can be up to 50 millisieverts per year. This would be places where, mostly in mountainous areas where radioactive elements have been brought close to the surface. So that's radiation from the ground that can cause an elevated radiation risk. So once again, in Louisiana, that's one thing we don't really have to worry too much about. We worry about other things, but we don't have to worry too much about the background radiation. I have a couple of questions for you. First, the activity of a radioactive source is measured in units of A, becquerel or curie, B, gray or rad, C, sievert or rim. The correct answer is A, becquerel or curie. So this is the radioactivity of a source. Remember that a becquerel is 1 decay per second, so 1 alpha decay or beta decay or gamma decay per second from the source. So the activity of a source is measured in units of A, becquerels or curies. Second question. A measure of radiation received that considers the biological effect resulting from the radiation is the A, becquerel or curie, B, gray or rad, C, sievert or rim. Now, both the gray and the sievert are units of dose, of radiation dose received, but the sievert is the one that takes into account the biological effect of the radiation. So the correct answer here is a measure of radiation received that considers the biological effect resulting from the radiation is the C, sievert or rim. Okay, what I have here is a Geiger counter, a radiation detector, and every time that it detects an alpha particle, a beta particle, or a gamma particle, it will make a click. So you hear that clicking noise every once in a while, every time that it actually detects a particle. So it's random. So there is actually radiation throughout this room right now. I also have a radioactive source. This is actually an old Fiesta-ware bowl, and this orange pigment here, the orange color, is actually uranium oxide. They used to use uranium oxide as a color to give you this bright orange color. Now this is actually radioactive. So this is sending off alpha particles, beta particles, gamma particles out of itself all the time. So it is constantly emitting radiation, and in fact some of it is actually hitting me. So I am actually receiving a radiation dose from this bowl. It's a very small radiation dose, not as big a concern as if I were smoking a cigarette, for example. Okay. So, but I'm going to talk to you about how to be safe around radioactive materials. There are 3 things that we want to consider. One is distance. The farther that you are from a radioactive object, the less radiation you will receive. So if I get very close, to the bowl, then a lot of radiation is hitting the counter. So the counter is receiving a large dose of radiation. But if I put some distance, then I'm receiving less of a dose. So the farther the counter is away from the bowl, the less dose it's receiving, and the farther away I am from the bowl, the less dose it's receiving. So if we pull back a little bit further, we're receiving less of a dose. Pull back further, not very much at all. So the first way that I'm going to keep myself safe is by keeping my distance from this bowl. So distance is one way to keep yourself safe. Just stay away from the radioactive object. Another way is to use shielding. I have some lead right here. And if I put the lead between the counter and the bowl, none of the radiation gets through. So all of those alpha particles, beta particles, and gamma particles are stopped by the shield. So that's, for example, why when you go to the doctor and you have to get, when you go to the dentist and you have to get an x-ray, you get a lead shield, a lead apron around the parts of your body that don't need to be irradiated. That radiation will actually stop the x-rays, just like it's stopping the gamma rays from this bowl. Mostly. A little bit's getting through. It's still going to click just a little bit, but not as much as all of that. So, to reduce the dose that you get from radiation, keep your distance from the radioactive object, or put some shielding either around yourself or around the radioactive object. That will reduce the radioactive dose that you receive. And the other is to not spend as much time with the radioactive object. Remember, all of those doses that I was talking about before were all a certain amount of dose per year, so per time. So the less time you spend with the radioactive object, the less radiation you will receive there. So the three ways to reduce your radioactive dose are to keep your distance, put some shielding between you and the radioactive source, or spend less time with it. So I think I've spent enough time with this bowl, so I'm going to put it away now. Okay, now that I put some distance between myself and that radioactive bowl, let's talk a little bit more about shielding. It actually takes a greater mass of shielding to stop a gamma ray than it does a beta ray, and it takes more shielding to stop a beta ray than it does an alpha ray. Now, an alpha particle can actually be stopped by paper or your clothing. They're not very energetic. They're very slow moving and not very energetic. So an alpha ray can be stopped by just a little bit of shielding. A beta particle will go through the paper, but a piece of aluminum will stop a beta ray, for example. Now, gamma ray being most penetrating, you tend to need some lead to stop gamma rays. So alpha particles are stopped with just a little bit of shielding, beta rays take more shielding, and gamma rays take even more. Which of the following types of radiation will not penetrate clothing? A, alpha particles, B, beta particles, C, gamma rays, or D, all have equal penetrating ability? Alpha particles are the least penetrating type of radiation, so the correct answer, which of the following types of radiation will not penetrate clothing? The answer is A, alpha particles. Next question. The most penetrating of the three common types of nuclear radiation is the A, alpha particle, B, beta particle, C, gamma ray, or D, all have equal penetrating ability. The correct answer is that the gamma ray is the most penetrating type of radiation. So the most penetrating of the three types of radiation is C, the gamma ray. Okay, let's talk about the time for radioactive decay. The time for radioactive decay is measured by the half-life. And every radioactive atom has a 50-50 chance of decaying in one half-life. So what that means is that the amount of radioactive material decays over time, and also the amount of radioactivity decays over time, because the amount of radioactivity is proportional to the amount of radioactive material. So if we start off with 1 kilogram of some radioactive material, and let's say that that radioactive material has a half-life of 1,620 years, so we start off with 1 kilogram. After one half-life, so after 1,620 years, half of that material has decayed. So we start off with 1 kilogram of radioactive material, half of it has decayed, so that leaves us with half of a kilogram of radioactive material after one half-life, after 1,620 years. Now let's think about the next half-life. Let's let another 1,620 years pass so that it is now 3,240 years since we started. Half of the kilogram has decayed. So we're now down to 1/4 of a kilogram. So in one half-life, we went from 1 kilogram to a half. In the next half-life, we went from a half to a 1/4 of a kilogram. So it is always half of what you start with that decays after one half-life. So half of what you had at the beginning of the half-life is what's left at the end of the half-life. So in other words, if we go another 1,620 years, then we start with 1/4 of a kilogram, we'll be left with half of that, or 1/8 of a kilogram. So once again, if we start with 1 kilogram, after one half-life we'll have a half of a kilogram. After 2 half-lives we'll have half of a half, or 1/4 of a kilogram. And after 3 half-lives we'll have half of a half of a half, or 1/8 of a kilogram. So the amount of radioactive material goes down by half every half-life, and the amount of radioactivity also goes down at the same rate. So the amount of radioactive material you have will decay very rapidly at first, so you will lose a lot of it at first, and it will be very radioactive at first, but then over time you have less material and the radioactivity decays away, but it takes many, many, many half-lives for it to actually all decay away. Okay, let's put this to work with some questions. The half-life of iodine-131 is 8 days. How much of a 28-gram sample of iodine-131 will remain after 32 days? So 32 days is 4 times 8 days, so that would be 4 half-lives. So we start off with 28 grams. How much will be left after 4 half-lives? Please pause and work that out, and when you have an answer, hit play and I'll work through it with you. Okay, I'm going to do this as a chart. So I'm going to put time, and we'll start off with 0 days, and the amount of iodine-131 is initially 28 grams. Okay, so after one half-life, after 8 days, we will have lost half of our iodine-131. So we've gone from 28 to 14 grams. So in 8 days, we go from 28 grams to 14 grams. After another 8 days, so that would be 16 days, we will lose half of the 14. So that we'll be left with 7 grams of iodine-131. After another 8 days, so that would be 24 days, we will lose half of the 7, so that would be 3.5 grams. And one more, go from 24 to 32 days. We will lose half of our 3.5, and that would be 1.75 grams. 1.75 grams. So if we start with 28 grams of iodine-131 at 0 days, at After one half-life, we'll have 14 grams. After two half-lives, we'll have 7 grams. After 3 half-lives, we'll have 3.5 grams. And after 4 half-lives, which is 32 days, we will have 1.75 grams of iodine-131 left. Okay, here's our last question for this lesson. Cesium-137 has a half-life of 30 years. A sample of cesium-137 has a radioactivity of 160 becquerels. How long will it take for the radioactivity to decrease to 10 becquerels? So remember that radioactivity also decreases by half every half-life. So how many half-lives will it take for the cesium to decay from 160 becquerels to 10 becquerels, and how many years is that? So please pause and work on this, and when you have an answer, hit play and I'll work through it with you. Okay, I'm going to do this one in a table as well. So we have time, and we have the radioactivity of cesium-137. So at time 0 years, the cesium has a radioactivity of 160 becquerels. So after one half-life, which is 30 years, the radioactivity will have decreased by half, and that will be 80 becquerels. 80 becquerels. After another half-life, so another 30 years, so that brings us to 60 years, we'll cut that 80 in half, and we'll be down to 40 becquerels. Another 30 years, that would be 90 years. Cut that 40 in half to 20 becquerels. And finally, another half-life, so another 30 years, so 120 years. We'll cut that 20 in half to 10 becquerels. And that's what we were asked. How long will it take for the radioactivity to decay to 10 becquerels? The answer is 120 years. That's our lesson on radioactivity and radiation. In our next lesson, which will be our final lesson for the course, we will talk about our favorite topic, which is energy. How do we get energy out of nuclear processes? Until then, think science.